Before the Second World War, if you wanted to elevate the ground floor of a domestic dwelling to raise it higher than the existing ground level, say, or to perhaps even out a sloping site, it was common to use a suspended floor of timber joists and floorboards. But after the war, there was a push to use different materials. In fact, by 1951, the Ministry of Housing manual stated that due to the shortage of timber, the construction of ground floors of wood joists and boards is not allowed, except on steeply sloping sites where the cost of a solid concrete floor would be prohibitive. And so, since then, what would have been voids under ground floors have regularly been made up with fill material.
Back in the 1970s, it was common for that fill material, the hard core, to be around 1.5 metres deep and more. Nowadays, the National House Building Council states that it is not advisable for concrete slabs to be laid on fill of more than 600 millimetres depth, unless approved by a civil or structural engineer. Suspended floors are still used, of course, and the Building Regulations, England and Wales, approved document C, recommends that a 100 millimetre thick protective layer, the oversight concrete, be laid under the suspended floor at about the existing ground level. This is laid to falls to ensure that water runs off and doesn't build up under the suspended floor. So, whether it's a solid floor slab or an oversight layer, each is laid on compacted hardcore directly on the ground. The two most significant hazards relating to hardcore fill material under concrete are settlement, frequently caused by poor compaction or the wrong type of material, and chemical damage, caused by a reaction between the fill or the ground and the overlying concrete. Well, this programme will look at the latter, at methods of protecting against chemical attack arising from what is called aggressive ground conditions and fill conditions.
And to help us do that, we're very pleased to have with us Dr. Brian McGee, who's Regional Engineer for the Concrete Centre. Very warm welcome, Brian.
Thank you very much.
Thanks for joining us. I'm intrigued by this phrase, aggressive ground. Let's see if we can, first of all, please, get a simple meaning from you as to what that is.
Well, it sounds rather sinister, doesn't it? But it's not actually too sinister. There are natural things occurring in the groundwater, in soils, in rock, that won't be harmful at all to people or to wildlife or the environment, but they can be harmful to concrete and the way concrete performs. Hence, the ground is classified as being potentially aggressive to concrete.
So, aggressive ground can be the actual soil, that's the chemical makeup of the ground conditions, as well as a poor mix of hardcore material. Now, in this programme, we're predominantly looking at sulfates, and we'll come on to ground conditions in a moment. So, firstly, Brian, why are sulfates harmful to concrete?
Well, concrete's quite a complex material. It includes cement, and when you mix cement with water, lots of very complex compounds and hydration products form, and they have a chemical background and a chemical nature. And when sulfate ions come into concrete, the sulfates can react with the chemical matrix of concrete and cause other things to occur or to develop, which might cause the concrete to perform less well.
And presumably there are different types of concrete.
There are different types of concrete, and there's different types of sulfate out there. Sulfate ions are negatively charged ions or anions, and they tend to combine with positively charged metal ions like sodium or calcium or potassium or magnesium. And when these ions come into concrete, they can react in different ways to cause different causes of deterioration.
You managed to make it sound fascinating. Now, hardcore, which is a term we're familiar with, and we understand what that means. But I understand there are different types of materials that can make up hardcore, and some that might contain sulfate. So what are we talking about here?
Yeah, hardcore can have lots of different histories, and there's lots of different types of hardcore that will, again, inherently include sulfates. So some examples might be waste from coal mining. So colliery spoils or colliery waste material might inherently contain sulfates or sulfides. Combustion ashes from the burning of coal or the burning of waste might inherently contain sulfate.
And what are the most common sulfates that we should be looking out for?
The most common sulfates are calcium sulfates, which occur in most natural grounds and groundwaters. Although, funnily enough, calcium sulfate isn't the most soluble sulfate, so possibly not the most aggressive of the sulfates. Magnesium sulfate or sodium sulfate is probably more aggressive in nature.
And presumably there are some sort of acidic compounds as well, which could pose a risk to concrete?
Yes, it's not just sulfates. There's other things that can occur naturally or occur in industrial hardcores, such as humic acid, which would be from decaying organic waste, carbonic acid, which would be water with carbon dioxide dissolved in it. They're not particularly aggressive to concrete. Sulfates, again, can be a problem in the production of sulfuric acid in the ground, which can be, it's quite a highly ionized acid, which can be quite aggressive again to concrete. And concrete's very stable naturally at a high pH. So anything that will reduce that pH can change the way concrete performs.
Yeah, and presumably brownfield sites must cause a tremendous problem because you must have lots of these compounds in the soil naturally.
Yeah, with brownfield sites, there's good guidance on how you should assess them and what you should be looking for, and things like sulfuric acid, things like chlorides, which will give an indication of the presence of hydrochloric acid, things like nitrates, which will give the presence or potential presence of nitric acid. These can all be present in industrial wastes.
So I get the feeling then that sulfate bearing hardcore should always be avoided as a matter of course. Is that the case?
Not necessarily. When concrete is designed properly and specified properly and constructed properly, sulfates can actually be dealt with quite well or very well. In addition, you can protect the concrete. So for example, concrete slabs can be laid on top of a damp coarse wearing layer, which will stop sulfates and moisture actually penetrating into the concrete. So there's perfectly well understood and well engineered methods of building in sulfate bearing soils and hardcore.
Okay, so that's hardcore containing sulfates. What about naturally occurring? Are there some places in the UK that are more prone to this than others?
Yes, there are, and there's some really good geological charts that can be looked at to see which soils and rocks typically will contain sulfates, and it really depends on the geological history of the soils. How they've been weathered with time will determine whether they contain sulfates. And in this area, London clays, for example, are a good example of ancient sedimentary materials that will inherently contain sulfates.
Now, when we're talking about naturally occurring, presumably, do we mean naturally, organically, by nature in the soil?
Yes.
Or are we also, but also what about from industry? I mean, particularly from sort of ancient industrial uses. Does that come under that general category as well?
Well, yes, but inherently everything comes from a natural background. So we mentioned colliery spoil, and the sulfates there would probably trace back to the presence of sulfides in the coal that was being used. So typically you can trace these sulfides back or sulfates back to some sort of a natural origin.
Well, that's what I was going to ask you, actually. How do you find out if they're present? How do you trace them back?
Well, the first port of call would be looking at things like geological maps, which give you a good indication as to whether they're likely to be present. But the only true way of finding out whether sulfates are present is by testing the soil. So every site should involve a thorough soil investigation.
What would just take me through it? So with the site analysis, how does this take place? Who's the person who does it, and how long does the testing take?
Well, testing is typically undertaken by specialist geotechnical engineers, and these guys will start off by doing a desk study, looking at the history of the site, where it's based. Is it likely to be overlying these naturally occurring sulfate-bearing soils? It will involve a walkover site survey, so they'll go and actually look to see whether soils are likely to contain sulfate. So reddish-brown clays are typically weathered clays, and weathered clays are will typically contain sulfates. Dark grey clays typically aren't weathered, but they may contain sulfides, which if the ground's disturbed, these sulfides may oxidize to form sulfates. So there's ways in which you can visually assess the ground, and then it will move into a testing regime.
And are we talking about a long procedure? How long does all this take?
Oh, it probably takes a matter of weeks, I suppose, to go from the start of the testing to the completion. So it's not overly onerous, and It's undertaken by specialist companies that do this for a living.
And what are the DS classes, the design sulfate classes? Because they were reduced a few years ago, weren't they?
Yeah, once the testing has been done on a given soil or groundwater, you understand the concentration of sulfates in the soil, so you can then class the potential aggressivity, if you like, of the soil in these design sulfate classes, which are laid out in the relevant design guidance documents. The design guidance for sulfate attack and aggressive ground has been around for decades. I think the first ever document was written in 1939. So with time, the industry's got a better understanding of sulfate attack. We've changed the way we proportion our concrete mixtures, for example, to deal with sulfate attack. So with time, we have reduced these limiting factors or limiting classes to be actually more conservative as we've better understood the nature of sulfate attack.
So from an architect's point of view, what should they be on the lookout for, particularly if they suspect that, say, for example, in an old floor slab, that they suspect there might be a sulfate attack?
Well, when sulfates come into concrete and cause problems, there's typically crystal growth involved. So I'll bore you slightly with the chemistry, but calcium sulfate, for example, might come into concrete, react with the calcium aluminate phases inherently within concrete to form something called ettrinite. And ettrinite, when looked at under a microscope, are crystals quite needle-like in shape. At a microscopic level, these crystals are growing, but on a macro level or a large-scale level, concrete will expand and crack, and you can actually physically see cracking of concrete if it's been damaged. If it's in a floor slab that's restrained laterally by walls or by foundations, the concrete slab may actually dome due to the expansion.
So is there any way of preventing this, and particularly if it's waterborne?
Yes, the guidance that's in place, it's a document called Special Digest 1, Designing Concrete for Aggressive Ground, will give really good guidance as to how the concrete should be proportioned so that it behaves perfectly well in these sulfate-bearing conditions. And it also gives guidance on how concrete can be protected further by either lining the concrete or by adding a sacrificial layer to the concrete. There's a number of different ways you can increase protection over and above the concrete inherently protecting itself.
Because it could have devastating consequences to footings and foundations, couldn't it?
Yes, it can do, and these problems typically have been spawned from an era when we didn't particularly understand sulfate attack. As you mentioned at the start, it was post-World War II where concrete was constructed in a different way to present time. We weren't using the same materials, or probably the nature of construction wasn't as good as it should have been. So the industry has evolved, and concrete designed and specified properly should actually be quite resistant. If laying floor slabs, for example, yes, a damp coarse layer will be there as a matter of course, if following the building regulations, and that will provide a really good protective layer for water and sulfate in that water actually getting into the concrete. There is something called sulfate resisting Portland cement, although actually in the UK we don't manufacture it anymore. It's not commercially available in this country. We have other ways of doing it, but sulfate resisting cement was cleverly designed to have quite a low content of calcium aluminates, which again I'm boring you slightly with the chemistry, but it was that phase inside the cement that reacts with sulfates when the sulfates come into the concrete to cause these expansive forces. So by reducing the calcium aluminate phase in the cement was inherently more sulfate resisting. But as I mentioned, we don't actually use sulfate resisting Portland cement to any great deal in this country anymore, and we have other ways of doing it. And we use Portland cement in combination with other powders such as fly ash or slag, and these materials are cementitious in nature, and they ultimately make the concrete behave very like a sulfate resisting Portland cement concrete.
Well, as we've heard, the simplest way of stopping this type of sulfate attack on concrete in aggressive conditions is to ensure that there's a physical separation between the concrete and the route of waterborne sulfates. As far as oversight concrete is concerned, approved document C, site preparation and resistance to contaminants and moisture, doesn't spell it out in any great detail, but the principle remains the same. We've discussed the conventional form of sulfate attack. With good detailing and good site practices, it is thankfully a minimal hazard these days, although older buildings can still be at risk. However, a second form of sulfate attack was discovered only 15 years ago or so. This is known as the thaumasite form of sulfate attack, TSA, and is a reaction within the concrete mix itself.
Brian, TSA,
Yes.
tell us about that. Is it as serious as it sounds?
Well, it's a form of sulfate attack. It's slightly different to conventional sulfate attack in that it needs a couple of additional parameters for it to actually occur. So conventional sulfate attacks requires moisture, a sulfate content, and typically aluminate phases in the concrete, whereas TSA requires additionally a source of carbonate. It requires a high pH, which is there anyway because concrete typically has a high pH, and it also requires quite low temperatures. So you boil all that together, a source of calcium and silica, a source of carbonate, a source of moisture, a low temperature and a high pH, and thaumasite can start to form.
So temperature is an important factor.
Temperature is quite important, yes. Like all chemical reactions, temperature has a part to play or has an influence. And research has shown in the laboratory, for example, that when concrete specimens are exposed to sulfate attack with a source of carbonate at room temperature, 20 degrees C, TSA isn't likely to form. As soon as those temperatures drop to below 15, it becomes more prevalent. And when you think that given ground conditions will potentially be below 15 degrees, I think Met Office data shows that at a depth of 1 metre under the soil, the range of temperatures is typically between 4 degrees and about 17 degrees. So there's a large proportion of the year and proportion of the country where the ground is below that temperature.
And presumably we're talking about geothermal heat and heat from buildings as well.
Yes, heat from buildings may have a positive effect if they actually raise the temperature of the soil immediately below the concrete. If they keep it above 15, then TSA shouldn't be an issue.
And are there some types of limestone that are more susceptible than others?
Yes, I mentioned that TSA requires a source of carbonate, and limestone would be a good example of a source of carbonate. Limestone is calcium carbonate. So if you use a limestone aggregate in the concrete, that can be introducing a source of carbonate.
So any limestone?
Predominantly, potentially, yes. But it doesn't have to be the aggregate. Carbonate can come from the soil or the groundwater because we have calcium carbonate naturally occurring in the ground. So you can get sources of bicarbonate coming in from outside. Or sometimes limestone filler is used in the manufacture of cement. So that's another potential source of carbonate.
So Brian, in general, can you just remind us what it is architects should be on the lookout for?
Well, it depends whether you're talking about at the start of a project, when they're specifying or designing a concrete structure in the soil, or whether they're looking at buildings or structure that they think are suffering from sulfate attack. So I'll start with the first one. If they're actually looking to prevent sulfate attack, they should be looking for good ground investigation work. They should be thinking about specifying the concrete, following the proper guideline documents, etc., and adding any additional protective measures, such as putting a damp course layer underneath. If they're looking at structures that potentially may be suffering from sulfate attack, then, as I mentioned before, quite often the signs of sulfate attack are expansion, so cracking of concrete, unevenness of surfaces. It may be cracking in walls which have been forced outwards by the concrete floor expanding. These kinds of things might indicate sulfate attack, although TSA, which we talked about, is slightly different in that it doesn't really cause concrete to expand. It's slightly more severe in that it causes concrete to soften. So quite often if inspection of concrete shows concrete that's quite soft and mushy potentially, then that would indicate sulfate attack.
And just remind us, Brian, why it is so important that architects do get to the bottom of this and do take action. How many cases have you been involved in? Perhaps you could give us some examples where a building has suffered from sulfate attack and you've had to, come up and clear up behind it.
Yeah, there's numerous cases around the country. We've talked about the use of hardcore, and there's many cases around the country where sulfate-bearing hardcore has caused problems in ground-bearing slabs of houses. There's been recent examples of foundations to bridges that have experienced some mild cases of sulfate attack. So sulfates are ubiquitous, you know, they're everywhere in the soil, so every site should be expecting to find sulfates, and you should really be designing the site, specifying the concrete properly to resist sulfates, which are probably going to occur.
I'm afraid that's all we've got time for. But before we go, I'd just like to point out that the spelling of sulfate in your study notes is, would you believe, correct. Like it or not, in 1990, the International Union of Pure and Applied Chemistry recommended that the official spelling of sulfur, pH, should become sulfur with an F to suit the American audience. And of course, we're not going to comment on whether we agree with that or not. Anyway, this programme on sulfate and concrete has been made possible by the intelligent contributions from Dr. Brian McGee of the Concrete Centre. Many thanks, Brian. And thank you too for watching. Till the next time, goodbye.